lack of fusion. Once you use up all its hydrogen helium fuel source. Eventually gravity wins and collapses it.
You should tell me this more in detail when I'm more relaxed.
Yeah,
Yeah, I'd like to listen.
I got also papers to go to NASA ATS website. Plus one in nature key. That will be soon.
So after today's homework, we have homework 11. The another homework 12, which will officially be due on May 3rd. But you can take some more time on that. Final exam. And we said final exam will be 60%. Not take home, like you have to do it at home and bring it. Right, you have to submit it during the exam period. So what do you call it? Bring home? Take home? Bring from home? And 40% in class. This will be 2 questions. This I don't know how many, so 2 questions. One problem probably, I don't know as such anywhere basically, but functional derivative seems to be a very good problem to ask. Like just there, we spent a good amount of time on that. Something which you have been using all the time. The question you can imagine I should be able to ask anytime, and something that you can answer immediately. It'll be a short question, something that you feel, or I feel that it doesn't require too much of preparation. It's just a background material after you clear this course. Any questions on that? Anything you would like to know?
The second question comes from the last part, and that goes on the
Last part means
after
I
that.
haven't thought about it so much. Let me not mislead you by saying anything. Spread it out. Again, my motivation would be something that is straightforward. Like if I ask something, for example, from this week of classes, it should be very something that you all know. For example, the orbit of something related to Kepler's law, which you already are familiar, and it should come out very easy even without significant amount of preparation. but at the same time, it should be related to this course. Does that help? So functional derivative seems to be a good thing for me, but then there are only 2 questions I can ask, so I'm not sure what. So functional derivative is a good candidate. How about that?
Yeah.
Like Lagrangian and Hamiltonian, given the Lagrangian, write down the Lagrangian equations of motions. That's a very good candidate. Like midterm 2, the inclined problem that I gave, which many of you got wrong for some reason, but I would say that's something standard, right? Or a pendulum problem, right? The Lagrangian for the pendulum, and write down the equations of motion, something like something which I expect should be relatively straightforward, not too lengthy, not too short. Something related to this course. Okay. Anything else want to ask?
When you get the take home part.
Oh, good question. Hopefully. Early, maybe because the questions I already know, I'm going to use it mostly to cover special relativity. Like we get only 1 week. So I will give some lecture links and basically ask you to do a couple of homework that is usually done on a normal lecture. So it should be possible to even get it out by the end of this week. It's just a matter of me sitting on it and doing, yeah. I'll try to do that by Thursday. How about that? Okay. Today's homework is something more relevant. I'm delaying it because I'm thinking that I had decided not to add any more questions. I'll just use last year's, but then I changed my mind. I want to do something for this homework. So that's why this homework might be delayed a little, maybe today evening. So I have to work on it. So, and after that, I will have to do that.
So homework 12 will be uploaded today also,
Tonight, yeah. Homework 12,
11 and 12.
oh, no, homework 11 will be uploaded tonight. And homework 12 and the final exam, the take home part, I should be able to do it very quickly. Like that will be just cut and paste and putting it. Homework 11, I'm working on it, or I'm deciding whether to, in the worst case, I will just cut and paste. Okay. But I'm gonna give it tonight is my shot, but I have an exam until 5 o'clock, so I don't think I'll be able to do until 5 o'clock. I have to work for your homework. Yeah, okay. So any other questions?
Question 2 of homework 10.
Question 2 of
Where
homework 10. Remind me?
that was with determining, solving the elliptical integral.
Oh, yes. Try not to do the integral. That's the complicated part in it, where I say in the brackets that you don't have to do it. If you want to do it, actually today's lecture might help in working out the integrals. But the best is to first go through it without doing the integral and keep it as an exercise for yourself that how to do the integral. Okay, so that's the easiest way to proceed. If the best way to do those integrals is using contour integrals that we did in math methods. That's one of the reasons why I don't ask you to do it, but I mean, I can tell you other ways too. Yeah, I may not be able to immediately say it right away, but
There's also this Weierstrass theorem. Which is another option.
Weierstrass theorem for doing an integral
No, the Weierstrass substitution,
substitution. Yeah.
where you substitute cosine of phi with tangent functions.
Okay, that's called Weierstrass theorem. Okay, the substitution. Yeah, I did know. Okay. Probably, yeah, if you can do it, yeah,
Well-
that's perfectly fine, yeah. Did it work out?
Very long.
Did it work out eventually?
Not quite, still kind of.
Okay. That's, okay, but yeah, yeah. Yeah. Ask me, yeah. I think here may not be the right place. Basically, I may not be able to fluently do it immediately. Because I usually do it using contour integrals, and this may not be the right place for it. I know at least few of you have not done contour integrals. Yeah.
Okay,
Yeah, meet me.
yeah.
Okay, good. Any other questions? Okay, so we were doing Kepler problem. And so Kepler problem is a two-body problem. It's a two-body problem involving the interaction is the gravitational interaction, but the gravitational interaction is so similar to the electrostatic interaction, except that one is attractive and one is repulsive when the charges are positive. Electrostatic is repulsive, gravity is attractive, except for that. It's very similar in structure, so all these things go through for, especially for hydrogen atom, because one is positive, one is negative, there it is exactly the same, so the equations are identical, and we boiled down to a situation where there was a radial coordinate, angular coordinate, radial velocity, and angular velocity, and there was a z component of velocity also, and there the correct argument is that there are two frames actually. There is a center of mass frame and there is a coordinate, relative coordinate frame. So in each of them, you can choose your x, y, and z, the origin or the velocity. So you can always get rid of that. It was not, I was not claiming that strongly in the last class, so you can choose that clearly. Once you choose that, you have, right, so everything is happening in a plane. Angular momentum is coming out of the plane. So it is primarily one direction. So that's a radial coordinate, that's a phi coordinate, and your Lagrangian is half mu r dot square. That's your radial kinetic energy plus 1/2 mu r square phi dot square. That's your angular kinetic energy, how much rotational speed there is. That's omega or velocity due to the angular speed, and potential energy is negative, so this becomes positive. And it is G m1 m2 over R, right? We have used or let's use our just to be able to use this relations even in electrostatics. Alpha could be G m1 m2, and if it was electrostatics, you just have to do Q1 Q2 over 4 pi epsilon naught. Just make sure that Q1 one is positive, one is negative. That's the relation, so it can be used for both cases. But we are in the context we are working on, it is purely gravity. So we are really thinking of Earth going around the sun. 1 over mu is a reduced mass, and that's 1 over m1 plus 1 over m2. Equations of motion is mu r double dot, that's your time derivative of the canonical momentum related to the r coordinate. That's equal to the, so it will be mu r phi dot square and minus of G m1 or alpha, right? Alpha. It's alpha over R. Oh, R squared, right? That's your gravitational force, attractive force. And this is sort of a repulsive force, but it's mostly because that's the centrifugal force, if you want. It is omega square R, right? So V square over R, that's the centrifugal acceleration, or when you flip it, it's the centrifugal force, if you want. The force, the equation of motion related to phi is you have a time derivative of the canonical momentum associated to phi, which is mu r square phi dot. That has to be equal to 0 because there is no phi dependence in the equation, and you immediately say that you identify that this is equal to the angular momentum. Use one equation in the other, and you immediately get an equation purely in the radial coordinate. So that's a second order differential equation if you want. So that's second order differential equation, second derivative of r with respect to t square, that's equal to divide this out, mu r, that is a mu r square, and which becomes let's see, Lz square over mu r cube minus alpha over r square. And that's a purely radial coordinate dependent differential equation. So that's a second order differential equation. Acceleration, the radial acceleration, if you want, is given in terms of the coordinate, radial coordinate in that form. We showed that this can be identified as a potential energy, right? So effective potential energy, if you want. So this is equal to the derivative with respect to R of an effective potential energy. And the effective potential energy will be R is equal to, we want to find a function whose derivative is equal to the right hand side of the previous equation and with the negative side sign included, and that's equal to 1/2 z square over mu r square. Think of it as like angular momentum. So this is p square over 2m, right? That's your kinetic energy. That's your angular momentum, and instead of mass, you have the moment of inertia. That's how it appears. So that's good to recognize. And you have minus alpha over r. Take the differentiation with respect to that, that becomes 1 over r square, and the negative sign makes sure that it gives you back the sign that you needed. Once you have it in this form, it is also good to recognize that if you can multiply r dot times r double dot, right? So I'm multiplying by r dot from the left. That means I have to multiply r dot on the right hand side also. Dr by dt and d by dr chain rule makes it a time derivative. This is nothing but the kinetic energy. So this gives you kinetic energy of 1/2 mu r dot square is equal to minus d by dt of u effective. That tells you that the kinetic energy plus potential energy is equal to a constant. Notice this is a second order differential equation. And you would like to have two initial conditions for that. And the initial conditions in this scenario will be mostly given in terms of the angular momentum, how much angular momentum you give, and the energy. That will be your two initial conditions. We can always talk in terms of initial position and initial velocity. That is usually the way we talk about equations of motion, but in Kepler problem, we say what is the angular momentum of the orbit and what is the total energy, which is equivalent to saying where is the position and the velocity associated with it. So that's your equation that is going to be governing our orbit. But before we proceed, let's look at what our potential energy is. Let's plot this. So if you were to plot this, you have a quantity that is Lz over mu, and it is 1 over r squared. It is mostly positive, so it increases. So when r is small, this is actually infinity, and minus 1 over r is negative infinity, right? So this is negative 1 over r, that's positive 1 over r squared. But whatever it is, when it is very close, this will dominate. So when r is small, this dominates. When r is large, the other one dominates because it is on it's in the denominator. So it is really small, but even though it is small, this dominates. So for r very much smaller than 1, let's say, right? It is 1 over r squared. And for r very much greater than 1, it is 1 over r, and it is actually minus 1 over r. Minus 1 over r is something like this. So for large r, the curve goes like this. For small r, curve goes like this. So probably it has to come down and then goes back. That's a possibility. And if you were to really plot this, this will really look like this. The moment you have a curve like this is u effective r as a function of position. The moment you have a curve like this, it has some characteristics. Where does it become a minimum? Let's call that r naught. And what is the value of the potential energy at that point? Let's call that u naught. So that's 2 points that we can recognize immediately. How will you find this position r naught? Take the derivative to be equal to 0. So find the derivative, d by dr, u effective of r, that's nothing but the force. Right, at this point, the force is equal to 0. That is the standard statement that the attractive force is exactly equal to the centrifugal force. The force associated with this has to equal to the force associated with the attraction. So d by dr is equal to minus so Lz square over mu r cube, and that's minus or plus alpha over r square. This has to be equal to 0. And that implies that r naught is equal to Lz square over mu alpha. So that will be one of the parameters that will be important in our solution. At r naught, what is your energy? So let's calculate u naught is nothing but u effective evaluated at r naught, which is equal to 1/2 LZ square over mu R naught square. And minus alpha over R naught. Let's do some algebra here. So that's 1/2 LZ squared over mu alpha times alpha.
U O V, V effective, U effective.
Huh?
The letter is U effective or V effective?
Oh, you're asking, I usually use U for potential energy. It is possible that some books use V. I like to use V because often we also have voltage. Right, electric potential, for example, if you're in electrodynamics, U overcharge is equal to V, right? So I try to be very consistent and I try to write U for potential energy. V will be U over charge or U over mass in this scenario. So I think overall I must have used U everywhere for potential energy. But I do know that textbooks use V as far as you're consistent is perfectly fine. Okay. So that's alpha, and so I multiply by alpha, so that's I now do R naught, and there is an R naught help. No. So that's all, right? So there is R naught squared, I suppose, correct? And minus alpha R naught, but LZ square over mu alpha is R naught. So one over alpha R naught cancels out. Minus alpha over R naught, that's equal to minus 1/2 alpha over R naught. Which means to say that there is this curve which actually is the minus 1/R, goes like this. This is exactly half of that. The U naught is exactly half of, but that's just for your information, and it has some, it is more generic than this, but even if you were to do other potentials, you will see this feature coming in. So let's simply write this as minus 1/2 alpha over R naught. Okay, any questions? Can I erase this part? Okay, so that's your two quantities, and while we are here, we can immediately ask, we have a kinetic energy plus potential energy is equal to total energy. Kinetic energy is always positive, it cannot be negative. So that means that energy has a minimum value. Since this has to be positive, so think of kinetic energy is equal to E minus U. U has a negative value possible, so that makes it positive. So E cannot be beyond that point. So there is a maximum value E can take, or minimum value E can take, and that will be this quantity. Right? So if you have energy less than this value, for example, if energy was less than you remember is negative, so that becomes a positive. If energy goes beyond that, it becomes negative, right? Because that by energy, I mean energy could be a negative number too. So beyond this point, you cannot have any energy because kinetic energy would be negative in that case. So that's the minimum energy. So this, if energy was this value, we will see that this will be a circular motion. Why? Because if energy is this, which is exactly equal to U, these two cancel out, kinetic energy has to satisfy that relation and it has to just stay there. Right. So again, let's see what is happening. So energy is exactly equal to this point. So energy is minus U. So let's say this is minus U naught, let's say, and this itself, U itself is minus U naught, so that's plus U naught, so that's equal to 0. So kinetic energy will be equal to 0. Yeah, this is the kinetic, radial kinetic energy is equal to 0. So there is no motion in the radial direction. It still has the angular motion because of the centrifugal term. So the angular kinetic energy is still there. It's only saying that the kinetic, radial kinetic energy is exactly equal to 0, which means that it will be in a circle. It is not going in, it's not going out. So this will be a circle. So that's a very hand-waving argument that this will be a circle. We will see this more concretely once we get the solution. Let's go slightly further up. So next possibility is that the energy is somewhere here. So energy is greater than U naught, which is a negative number, and it is less than 0. So it's somewhere between these two points. If energy is so much, so kinetic energy plus potential energy can balance each other, they can redistribute each other. So think of a particle that can start from here, that goes here, that can go in there. When it means that there exists a point at this point, which is what is shown, the kinetic energy will be exactly 0, because again, energy will be exactly equal to potential energy here. At this point, it has to come to a rest. It can go down if it is here, it gains kinetic energy, reduces potential energy, gains, so it can redistribute kinetic energy and potential energy. What it means also is that there is a R maximum it can take, and there is a R minimum it can take. So there is a minimum radius, there is a maximum radius. Think of an elliptic orbit. Earth comes close, there is a minimum value. Earth goes far, there is a maximum point. That's your R minimum and R maximum. If you were to think of an ellipse, we haven't shown that this is an ellipse. If this was Earth, so that's your R max, and that's your R min. It doesn't have to be of this case at all. This is a closed orbit. You could also have scenarios like this, right? If I show this, there is a minimum value, right? R never goes below a certain value. R doesn't go beyond a certain value. These are supposed to be ellipses that does not come back to itself. That's not a good diagram, but think of a elliptic orbit that is precessing as it is going. So it doesn't, so there is a minimum value in the sense that it doesn't go inside of this. There is a maximum value inside in the sense that it doesn't go outside. So always you will have an R minimum and R max whenever energy is in between these 2 points. And this is what we will see is the case of an ellipse. It is also possible that energy can be exactly equal to 0. What is the characteristic of that point? There is no maximum value. There is a minimum, but the maximum value is no more there. And that particular case will be a parabola. There will also be a scenario where energy is larger. Again, there is a minimum value. There is no maximum value. That will be hyperbola. But it is not very obvious why circle, why. I only told you that there is a minimum value, maximum value. I haven't actually proved to you that this is circle or an ellipse or arrow. For that, you have to have the equation of the orbit that has to come out, and the real orbit equation has to tell you that. But that is what is going to happen. So in terms of these two quantities, let's try to write down our equations of motion. So that's your equation of, or let's go back here, right? So that's our energy equations, right? Let's rewrite it in terms of these two variables. So let's go back to this equation. Or first, let's rewrite our U effective, right? U effective R in terms of these two equation is 1/2 LZ square over mu alpha. I've divided out by alpha, then I multiply by alpha, divide it out by R naught, and that is an R naught over R squared. And minus alpha over R naught times R naught over R. I'm bringing in the parameters that we need. That's nothing but R naught. And 1/2 and alpha R naught, alpha over R naught is U effective. So I can write this as minus of effective R naught. So I have pulled out a minus 1/2 alpha. So that makes it plus, right? 2 times R naught over R. The second term I write first. And this is minus of R naught over R whole square. Right, that should be correct. So I written effective potential in terms of these two values. Let's also do the same thing for the kinetic energy term. So 1/2. Do that here. Oh, change the camera. So 1/2 mu R dot square, that's the kinetic energy. So that's 1/2 mu dr by dt can be written as d phi by dt times dr by d phi whole square. Phi dot, use angular momentum construction. So that's equal to 1/2 mu LZ over mu R square. LZ over mu R square with dr by d phi square. Again, we want to convert everything in terms of the parameters that we chose. So that's mu times R cube, or R raised to 4 actually, dr by d phi whole square. Do the same idea. LZ square mu alpha over R naught and R naught over R raised to 4 dr by d phi whole square. That's an R naught. So R naught square. So it is minus U effective of R naught. And then I have R naught square over R raised to 4 dr by d phi. Let me write that as, pull that inside, R naught dr over R square d phi whole square.
Should be mu square. That's it.
Because as it cancels one of the mu's, right?
Okay.
Right, mu and mu. So. Think so.
So like in the last, come to the last. How did we come from?
Oh, how did we? So let me do that here. So this is equal to, so that's R naught, right?
Yeah.
So R naught, so this is 1/2 alpha over R naught times R naught square over R square, correct? This R naught goes in here. And minus alpha over R naught times R naught over R. So pull out a 1/2 or minus 1/2 alpha over R naught. Right, so that's minus R naught square over R square and plus 2 R naught over R. And minus 1/2 alpha R naught is what I called U effective R naught. And this one is what I wrote here. So that's your potential energy. And the kinetic energy I just now wrote in terms of the new variables. That's this. So my equation here, this factor here looks like minus U effective R naught times R naught dr over R square by whole square plus. Is it plus? Yeah, no, minus, right? Minus. Really, minus? Yeah, no, this is plus, right? Because minus 1/2 alpha naught is U effective, right? So this should be plus. So good that you asked me to do it. So you could check. So this is plus. Notice this. This is a correction here. That's plus.
I might need to turn the camera.
Oh. Thank you. Very good. So correction that is this was a minus. Earlier I wrote this as minus and now that's plus. That's for the audience in the future. Okay, so anyway, thank you. So yeah. So the kinetic energy, which is the plus potential energy, which is active R naught, and we have 2 R naught times R naught over R minus. Let me write this the opposite way. Let me write it as negative. So that both have negative sign. Think so. And then I can write this as R naught over R whole square plus 2 R naught over R. You can see that this is kind of it's trying to be a complete square, right? But it's not a complete square yet. That's equal to the total.
This minus, right? 2R not 2R should be.
Oh, yeah, minus. Okay. Minus. Yeah. Right. Let me divide out by the minimum potential energy, a minimum value for the potential energy. So there is a scale for energy, that's a ratio of that. So then we have equation of this kind. Plus R over R the whole square minus. If I add up 1 there, that becomes a complete. So I'm going to leave some room there. That's equal to dividing out by minus. So this is again I will leave some room here. That's minus of E over U effective or not. Remember, this is a negative value, or the U effective, the minimum value is negative. So this quantity actually is positive, right? Because the minimum value is negative. Right. Just to make it a complete square, add a 1 there. just a manipulation technique. Let's add a 1 there, and now I have a square of two quantities. Two quantities that are positive. So that's R naught over R minus 1 the whole square. Right. Two quantities that are positive, it will give you a positive number. So let's call that E square. This will be very soon related to the what is called the eccentricity of an ellipse. Right? That is what we covered, but what is it equal to in our, that's just a redefinition for our purposes. That's 1 minus energy over effective. And remember again, it depends on if energy is negative. This is also negative. This can be a positive number, right? So that is how it comes out. But it can be like whatever it is, E square will always be positive. So remember, energy is always greater than this value. So that is positive. That's your equation. This is ready for integration at this point. So let's rewrite this in a point because we want to write dr over d phi, right? So let me put this on the other side and make this prepare myself for this. So this is r naught dr r square d phi is equal to e square minus, it doesn't matter how I write this. So this is 1 minus r naught over r. That's how typically we'll write it. And I can take a square root of this. So all this was dressing up the equation, the same differential equation. The first differential equation that I got for the energy equation, I manipulated it, dressed it up in our own coordinates, but there is nothing new between this and this equation here. This is basically conservation of equation, conservation of energy equation in the coordinates of R naught and energy. Right? This is where I do the actual integration. So I put d phi on one side, like separation of variables, right? And R naught times dr over r square times 1 over e square is 1 minus r naught over r the whole square. I have separated the variables. Once I have separated the variables, I can integrate. And that integral is a very easy integral. Remember again, there are only 2 steps in this whole problem. Even though it took half an hour, most of the time I was starting from the energy equation. I wrote the energy equation in this form. It was just dressing up. Right? I was manipulating cleverly in a particular form, and then I integrate. That's a differential equation. I'm integrating, and this integral is just one step. So I'm going to do the integral in just one substitution, and the substitution is going to be, so 1 minus r naught over r is equal to, let me substitute minus e cosine theta. That's a new variable I put in. Remember, phi is our variable. The polar coordinate is phi. This is a substitution variable. Like it is a temporary variable, it will go away. Okay? And it doesn't matter whether I use minus or plus. Let me use minus. Right? It doesn't really matter, but I will be using minus for my substitution. If you use plus, that's okay. Your solution will change slightly, but it may not match the homework solution that I have written up. If that's your substitution, what's your dr? So that's minus r naught dr over r square. That's my differential, and that's equal to E will be, the cosine theta will be sine theta, but with a plus sign. This is the plus, right? Yeah. Plus. And this is plus E sine theta. Theta. Right. And so this was all done in such a way that it becomes straightforward. This is already ready-made for us. E sine theta. So this integral is phi is equal to integral of E sine theta divided by the denominator. You have E square. This is nothing but E square cosine square theta. That's also E sine theta. So that's equal to the integral will be theta, but there is an integral constant. Let's call that phi naught. Okay. So we've done with the integration. In one stroke, we solved the differential equation. So our solution is phi is equal, or phi minus phi naught is equal to theta, right? But that's in terms of this temporary variable, put it back. We have to go back and substitute it wherever things comes in. So if I put this in here, I have 1 minus R naught over R is equal to minus E cosine of, instead of theta, put it phi minus phi naught. And that's my solution. Right? Let's rearrange this. We are interested in R, right? How is my radial coordinate changing with angle? Right? That's my solution. So I need my R. So R as a function of angle will be equal to R naught over 1 plus E cosine of phi minus phi naught. After the quiz you did today, that should be familiar. What is that? That's the equation of an ellipse, or for that matter, any conic section. If so, this is a conic section, and if E is equal to 0, right? If E is equal to 0, R is equal to R naught. Radius is fixed. That's a circle. Okay. Radius fixed is a circle. If E is less than 1, greater than 0, and we argued the same thing with respect to E, the total energy E. Earlier we discussed in terms of that. Now this decides that this is an ellipse. E is equal to 1 is a parabola. And E greater than 1 is a hyperbola. These are all solutions of Newton's orbit, and these are the actual orbits that you see in Kepler problem. Most of the planets are ellipses. Parabola is very rare. You have to be having a very perfect scenario in for that case. For that matter, even a circle is very rare. You don't see circles very often, but hyperbola and ellipse is very common. These two are rare because you have to satisfy the condition so perfectly. It is very rare in that. So let's say we are in a scenario where it is an ellipse. So let's choose our elliptic orbit. So that's your ellipse, and ellipse has 2 focal points. So that's your coordinate system. And whenever we write this equation, it is assuming that the origin is at one of the focal points. Like it is not at the center of the ellipse. It is either here or there. You can choose either one of them. You can choose this or that. There is nothing wrong in either one of them. But I'm going to choose this. And that's because one of the reference books that you use, Landau and Lifshitz, he used it on the right side. So this is going to be your origin. That means to say that that's your R. So this is your R if you want. That's not a vector, so let me not. So that's my R. Where is your angle phi? That's my angle phi. Immediately you ask the question, when do you, so there are this phi naught, R naught, and E that are coming into picture. So let's choose when your phi is equal to 0. So let us choose when phi is equal to 0. This is the minimum value the radius can take, right? This is the minimum, that's a maximum. Right? If you have an elliptic orbit, that's even if it is a hyperbola, you can always have that minimum value. So when phi is equal to 0, let's say R is equal to a minimum, R of 0 is equal to R minimum. What is the minimum value this can take? Whenever the cosine value is a maximum, right? Cosine value is a maximum when it is +1. It's a minimum when it is -1. So R minimum will be equal to R naught over 1 plus E. If I require that condition, I immediately say that that implies that phi naught is equal to 0. Right? By choosing this, what I've said is that phi naught has to be equal to 0. That is just setting my coordinate system. I could have started my phi from anywhere I want to, so I just set that to 0. It also tells me that immediately phi R of pi is equal to R naught over 1 minus E, which is also the maximum value. Okay. I have my solution there, so I don't need this. So let me do the following calculation. I want to do d phi starting from the minimum value to the maximum value. So this is R minimum to R maximum. So for any orbit, there will be a minimum value and a maximum value. If it's a perfect ellipse, they will be on the opposite sides of the orbit. So you have, this will be minimum, that is maximum. That need not be the case. Imagine there are scenarios when it will start from here, that's here. So it starts from here, the maximum it will get is somewhere here. So it comes back down here and then goes in here. So this can do this. Is that clear or not? Hopefully. So this is called precision. Is that clear what I'm doing? For a Newtonian orbit, what we have shown is that this is a perfect ellipse. There is no precision. But what we would like to do is that, what if we take care of Jupiter? Or there is really some other mass that shows up at the center of Sun. is it possible to disturb this? What if the Newton's law is not perfectly right? Maybe there is a small correction to Newtonian orbit, then we should see a correction in the orbit. And it is seen, historically, what happens is that Mercury does not follow a perfect ellipse. And we are not able to accommodate for it using Newtonian physics, the rotation that it makes or the precision that it makes. So let's take care of that. So first we have to define what precision is. So precision is going to be start from R minimum and go all the way till R maximum. R maximum could be not necessarily right across from the orbit, it could be somewhere else. So go from R minimum, go to R maximum, and then multiply it by 2. Okay, so that means you go here and then you reach here. But this one, it is not really 2 pi. If it was 2 pi, then the precision is 0. Subtract out 2 pi, and this is what you will call the precision angle. Precision, check the spelling, precision angle. Okay, is that clear? Any questions there? I start from, this is my R minimum. I go to the R maximum. And then I make it twice. So when I make the second round, this becomes the minimum. That's my maximum. So I reached here. So 2 times, when I say 2 times this, I have reached here. Which could be either on the right ahead of this or below. Whatever is the difference, that's what I say is the precision angle. Okay, so that's my 2 times d phi. And it should have been 2 pi. In this ellipse, how much, what will it be for our orbit? They should come out exactly 0, right? Because it's a perfect ellipse. Like in our case, this will come out to be 0. And now we will disturb it later on, next lecture, and show what could be, what it is for the Mercury. So this is equal to minus 2 pi times 2 times R minimum. Our minimum is R naught. Over 1 plus E times R naught over 1 minus E, right? And d phi we said was, remember, I think d phi was R square, no, R naught dr over R square divided by E square minus 1 minus R naught over R whole square. Right. Basically doing that integral again, except that now it's a definite integral. Right. We can actually do that right at this stage itself in principle, but just for making it clear, I'm substituting d phi with dr and making it a definite integral.
So the 2 pi is inside the integral or just?
No, this is, if this helps,
Then in the second step, it should be plus.
plus. So, yeah, plus. Meant to write it, yeah, thank you. Oops, yeah, thank you, yeah, that can be confusing, very confusing, yeah, okay, this is better, okay. Okay, so, again, what is the answer you expect in this? What should this be for this orbit that we are doing?
0.
It should be 0, right? So it's just a check we are making so that later on for another orbit, we can actually get a non-zero answer. So this is equal to minus, so make the same substitution, right? So minus 2 pi plus 2 times, make the same substitution. 1 minus R naught over R is equal to, we said minus E cosine phi or cosine theta. Cosine theta. So this is R naught dr over R square is equal to E sine theta d theta, right? But now we have to worry about the limits when r naught is equal to when r is equal to so much. So I have 1 minus r naught over r is equal to r naught times 1 plus e is equal to minus e cosine theta. R naught cancels out 1 minus 1, so that's minus e is equal to minus e cosine theta. That means theta is equal to 0. Correct? So this is equal to 0. And when r naught is 1 minus e, so this is 1 plus or minus, I can say. So this will be plus, minus, or plus. So this will be theta of 0, and this will be equal to pi. So this will be pi. This is e sine theta, so that's e sine theta, e theta, and this one is again e squared minus e squared cosine square theta. So e cancels out, sine theta cancels out, so that's minus 2 pi plus 2 times 0 pi theta. That's equal to minus 2 pi plus 2 times pi, which is indeed is equal to 0. Sort of a trivial calculation at this point. But now what we want to do is that we'll come back and do this. Is that what if Newtonian gravity is not perfectly correct? Historically speaking, what happened is that Newtonian gravity was very successful immediately in right after he proposed it in 1666 to 87, yeah, 87, and it was extremely successful, and they started predicting what will happen, especially the transits, whenever Mercury used to go in front of the sun, so you could see a small dot going in front of the sun. So they used to start predicting it, but it turned out that some of them were not so perfect, and that was Mercury was an example. It was not working out very well. So the moment it was not working out, they used to say, oh, we have to take care of Jupiter's orbit, we have to take care of Saturn's orbit. So you could take care of all the orbits, and still there was no room for any correction for explaining why Mercury should be having a perihelion shift. And that immediately makes you doubt, maybe Newtonian gravity is not correct. Right? Is it possible that this is not really 1 over r, that is an exponential of, let's say, minus alpha or kappa over r, or kappa times r, let's say. Kappa times r, or something like that. And so we will see if we make some corrections in that, how will this change, can be explained that to a certain extent. That will be what we'll do next time, and then we'll stop with that. Thank you. Okay, good time.